Picture this. A city trembles, the earth writhes violently, modern steel skyscrapers sway dangerously, concrete cracks and, crumbles. But somewhere in that same landscape stands a wooden structure, ancient, intricate, elegant, barely swaying, completely unshaken. No nails, no bolts, no glue. Just wood fitted so precisely that it dances with the earthquake rather than resisting it. This isn't fantasy. This is the Edo period. Welcome back to The Lost Tactician, where we uncover the forgotten wisdom of those who survived through ingenuity rather than force. Today, we're unlocking the architectural genius that allowed Japanese wood joinery to laugh in the face of centuries of seismic devastation. Why do modern buildings fail where ancient ones stand? Stand in front of Tokyo's 5-story pagoda at Horyuji Temple, and you're looking at a structure that has survived over 13 centuries of earthquakes. Meanwhile, concrete buildings from the 1970s collapse in the same seismic events. The contrast is, honestly, brutal. When Turkey faced a 7.8 magnitude earthquake in 2023, modern reinforced concrete structures pancaked while ancient wooden buildings in nearby regions weathered the same forces with minimal damage. The answer, really, lies in understanding what an earthquake actually does. Modern engineering tends to treat earthquakes as something to resist, with rigid foundations, immovable frames, and metal connections designed to lock everything in place. But you know, this philosophy kind of misunderstands the problem. An earthquake doesn't just push, it shakes and oscillates. A rigid structure that refuses to move is, honestly, fighting the wrong battle. It ends up concentrating all that seismic energy into specific points until, well, connections fail catastrophically. Edo period builders understood something we've perhaps forgotten. The best way to survive an earthquake isn't to stand unmoved. It's to move with it. This, in turn, birthed kigumi, Japanese wood joinery, a philosophy of flexibility, and a practice of precision. A legacy of survival that honestly challenges everything we think we know about structural engineering. Unlocking the joinery code means stepping into a traditional Japanese miyadaiku workshop, a master carpenter's space, and, well, you won't find blueprints there. Instead, you'll see wood, hand tools, and really knowledge that's been passed down through generations. The joinery system developed over centuries isn't just a single technique. It's, in fact, an entire language of connection, with more than 30 distinct joint types, each one carefully refined for very specific purposes. The fundamental concept is interlocking. Male and female components, cut with mathematical precision to fit together without gaps. A mortise and tenon joint is most recognizable. A projecting tenon slips into a corresponding mortise hole. But you know, the variations are staggering. Dovetail scarves interlock like fingers gripping each other. Complex three-dimensional corner joints distribute forces across multiple planes. And, well, self-tightening wedge joints, like the kanawatsugi, actually strengthen under pressure. What's extraordinary is the precision. When you examine an Edo period joint under close inspection, the fit measures in fractions of a millimeter, achieved with hand tools and substandard iron. Master carpenters understood that wood naturally expands and contracts with humidity and temperature. Joints were designed with calculated clearances to accommodate this movement while remaining functional. This really reveals the genius. Joints were designed to work with wood's nature, not fight it. The material selection process alone could take months. Timber was carefully chosen based on grain structure and origin. Then came seasoning. sometimes decades of controlled drying, until the wood reached perfect equilibrium. Only then would timber be cut for critical structural elements. The master carpenters possessed almost mystical understanding of wood itself. Imagine for a moment a pagoda during an earthquake. The ground shifts violently beneath it. Now, most of the tower's mass is actually concentrated at the top, which, creates these enormous inertial forces. In a rigid modern structure, all this energy is transmitted downward through stiff connections, until, something catastrophically fails. But a pagoda built with kagumi, it does something quite different. It bends, it sways, each floor moves just a little bit relative to its neighbors. The thousands of individual joints throughout the entire frame each experience tiny bits of friction and, slight movement. Collectively, they dissipate the earthquake's energy like thousands of shock absorbers all working together. This principle is called energy dissipation, because as wooden joints move microscopically against each other, friction actually converts kinetic energy into heat. Self-tightening joints, interestingly enough, actually strengthen as shaking intensifies, gripping even more firmly, quite the opposite of modern fasteners, which tend to loosen, corrode, or fatigue over time. Many Edo period structures employed another brilliant strategy, deliberately loose-fitting wooden brackets connecting each floor to the frame. This allowed upper levels to move semi-independently of lower levels, preventing the entire structure from moving as one rigid mass. The most famous pagodas featured a central pillar, the Shinbashira, hanging freely from the roof, anchored only at the top. This pillar doesn't support the building's weight. Instead, it acts as a shock absorber, swaying with the building and further dissipating seismic energy. The result is choreographed response to disaster. The structure moves in a controlled snake dance, twisting and swaying in ways that would terrify the unfamiliar. Yet this movement is precisely what keeps it standing. What astounds modern engineers examining these structures is execution, achieved tolerances measured in fractions of millimeters with hand tools forged from substandard iron. Create joints fitting so precisely that hundreds work in concert without metal fasteners or adhesives. Do this repeatedly for centuries across countless structures. The variety of joint types reflects deep problem solving. A corner joint bears different stresses than one connecting beams of the same orientation. Connections high in structures experience different forces than those at the base. Traditional carpenters developed specific joints for each situation. Equally remarkable, these structures improved with age. As wood naturally stabilized over decades and centuries, joints seated more firmly. Metal fasteners, by contrast, corrode, fatigue, and loosen. Wood joinery could function for 1,000 years with minimal maintenance. The oldest wooden structures still standing are Japanese temples and pagodas, many predating any comparable wooden structures on Earth. Traditional joinery declined with modernization. When Japan embraced Western construction methods in the late 19th century, the tradition of miyadaiku faded. Young people no longer apprenticed for 15 years. The assumption was that modern materials and techniques were simply better. For rapid urbanization, they were. But as earthquakes continued and engineers studied why ancient structures survived where modern ones failed, something unexpected happened. Scientific understanding of seismic engineering converged with ancient wisdom. Researchers discovered that flexibility, controlled movement, and distributed energy dissipation were keys to earthquake survival. The principles weren't folk wisdom, they were sophisticated engineering expressed through wood. Today, there's a quiet renaissance of interest in traditional joinery. Contemporary architects and engineers study these ancient techniques to learn principles adaptable for modern materials. Japanese temples are being rebuilt using traditional methods, employing remaining masters and training young apprentices. Research institutions publish detailed analyses of joint performance. Modern carpenters blend traditional joinery with sustainable building materials. The implications extend far beyond preservation. Trees absorb carbon dioxide. Wood stores it throughout a building's life. Wooden structures don't require energy-intensive cement and steel production. A building lasting 1,000 years without major maintenance looks very efficient indeed. If it survives earthquakes threatening our densifying cities, the advantages multiply. The story of Edo period joinery asks some really fundamental questions. Instead of asking, how can we make something unmovable, they asked, how can we make something that survives by moving? You see, they mastered flexibility over rigid strength. We stand at a moment when this wisdom feels, well, increasingly urgent. Cities are densifying. Climate change is intensifying seismic activity. Structures must last longer and perform better than ever before. The answer, honestly, often isn't hidden in the future. It's waiting in our past. The 5-story pagoda at Horyuji still stands. It survived earthquakes, wars, fires, and, believe it or not, 13 centuries. It really testifies to what humans once knew, and what we might learn if we're willing to look beyond our era's certainties. If this sparked your curiosity about ancient wisdom solving modern problems, go ahead and subscribe to The Lost Tactician. Here we excavate survival's practical genius and the deep ingenuity of those who built to last. Like this video, share it, and hit subscribe. Because, honestly, the greatest breakthroughs often come from understanding what those before us already knew.